Welcome back. Now in the last video, we turned a small section of our image, namely the top row, into patches. And I issued you the challenge of trying to patchify the whole image, because that's the first step in the patch and position embedding, is turning our input image, a single input image, into patches. And then we got to flatten those patches and then turn them into some kind of embedding. We'll do that flattening and embedding projection later on. But now let's focus on how do we visualize this image of pizza, and now your image might be different because the data loader is random. So way back up here, just keep that in mind. The image doesn't really matter. It should work with any image. So this may be an image of steak or sushi. Let's keep going. The code should still work. So what we're going to have to do is this one we iterated through the width dimension. And I gave the hint that we're going to have to iterate through both the width and now the height dimension. But the overall code here is going to be quite similar. So let's go here. We'll set up code to plot whole image as patches. So we'll redo the image size equals 224. Or in fact, what we might do is just copy this down to here. So image size equals 224, patch size equals 16, number of patches equals image size divided by patch size. And we will go here, assert image size. We want it to be divided by patch size and then equal to 0. And then image size must be divisible by patch size, otherwise we'll get uneven patches. And let's print out some information here so we know a little bit about what's going on. Number of patches per row. So num patches, and then we'll go to a new line, we'll tab in, print out here, and then we'll go number of patches per column, which will be num patches as well. So we're doing the whole image now. Then we'll get another line and we'll go total patches, which will be equal to num patches times num patches. Num patches sound like a rapper name. Num patches, patch size. Once we've built a vision transformer, we'll be able to call ourselves num patches times patch size pixels. So a whole bunch of information here about what's happening, but let's just see what it does. So we should have number of patches per row, 14, number of patches per column, 14, and total patches is 196. Where does that number come from? If we come back up here, we've already calculated that, number of patches. So we need to figure out later on how to turn each one of these patches into an embedding of size 768. Well, let's not get ahead of ourselves. We're trying to visualize one single image here. And then each individual patch is 16 by 16 pixels. So you're ready? Let's now create a series of plots, a series of subplots that is, to plot each one of our image patches. Fig axes equals plt.subplots. And this time we're going to have a number of rows, which will be equal to image size divided by patch size. And we're going to have a number of columns, which was going to be equal to the same thing, image size divided by num patches, or patch size, sorry. Then what do we need? Well, we need a fig size, and let's just turn this fig size to num patches and num patches. And then we'll go share x equals true. So we share the x axis information and we'll share the y as well. So that is, we want to share these labels here. Share x, share y. So let's keep going. We've got a subplot there. What happens if we print this out? It might take a little while here because we're trying to visualize 196 patches or 196 plots. You'll see down here, we've got executing time. Unless there's an error. There we go. Okay, so that took a little while, it took about 40 seconds, but that's because we're working on Colab here and it's got about 2 CPUs. I believe Matplotlib, if you're plotting lots of plots, can be quite CPU intensive, but the good thing is that we've got them set up. And this is just for visualization purposes. this is not going to be the same code that flows through our model. So loop through the height and width of the image. So for I, we will start with the patch height. In enumerate, we want to go through a range of 0 to image size using a step size of patch size. So this is going to be iterate through height. So this is our height dimension here. We want to break our image, our single image, into patches. So we want to go through the height and then through the width and create patches of size, patch size. So now let's go for I patch width in enumerate. You may already have code similar to this because that was the challenge for the last video. But if not, that's fine. That's why we're doing it together. Now let's plot the permuted image on the different axes. So what we actually might need to do is, because we've got I above, we need to change this one to J. So we need this one to be separate so we can separate patch height and patch width. And because we've got 196 axes, so 1, 2, 3, 14 by 14 is 196, we can index on each one of those axes by going axis I, J. So this is going to, for the first one, it's going to be 0, 0. And then for the next one, 0, 1. And for the next one, oh sorry, this way. 0, 1, 0, 2, 0, 3, 0, 4, etc. 1, 0, 1, 1, 1, 2, 1, 3, and so on. So let's now go ax ij im show, and we want to go image permuted. Now here's where the trick comes for indexing. So the first dimension is patch height, and we want to go patch height to patch height plus patch size. So this is going to iterate through the height dimension. Then on the next one, we want to go on the width dimension. We want to go patch width to patch width plus patch size. And then finally, we want to get all of the color channels. So iterate through width and then get all color channels. So a little bit going on there, but nothing we haven't done before. All we're doing is we're expanding this to loop through not only the width, but the height as well. So now we've got the height axis in there, or height dimension of our image tensor. So now we can set up a little bit of information. So set up label information for each subplot. Now each subplot, of course, is also known as a patch. So we'll go axis ij, get the current axis, and we'll set the y label. We want the y label to be I plus 1. And then this is a little bit of formatting here. Because this is a machine learning cooking show, I've actually cooked up this plot earlier. So I'm just going to make the y labels look pretty. We can do this without it, but they don't look as good. Horizontal, now alignment. That's probably definitely a spelling error, but we want this one to be vertical alignment. We might get some spelling mistakes wrong here, but if we do, that's all right. So now we go axes ij to clean up some things. We want to go set X label. We'll go J plus 1. So we've got I and J. So the Y label is the I, X label is the J. Then we'll go axes ij dot set X ticks. Otherwise, we'll get all of these little ticks here. Just removing those. And then axes ij set Y ticks. We'll do the same for the Y ticks. And then finally, we'll go axes ij and make sure the labels are on the outside, label outer. To figure all this out, by the way, took a fair bit of exploring through the Matplotlib documentation. So don't think this just comes naturally to me. I definitely had to do my research. And then we'll set up a title for the plot. So fig there's an attribute called, or a method called super title, which is going to go above the whole plot. So we'll go class names, we'll index on the label. So whatever image label that we're working with will appear at the top. And if we've written the code correctly, it will be patchified. So just remember, your image may be different to mine because the data loader is random. And then we'll go plot.show and see if we have no errors. Fingers crossed. So this, again, may take a while because we have to create 196 individual plots. And that's going to be a little bit CPU intensive for our Colab workspace. So I'm just going to fast forward this until it works for me. Boom. There we go. Pizza patchified. So look at all those little image patches. We turned our image into a patch of smaller images. I don't really know how to describe that. But you can see here we've got 1 to 14 rows and 14 columns, which equals 14 times 14, which equals 196. Now if we go back up here, how many patches do we have per image? 196. So we've just figured out how to turn our image into patches. But our code is quite verbose. And if we had to wait that long for every single image, like going through a neural network, if we're working with thousands of images, well then our network's going to be untrainable because it's going to take too long per image. So you might want to think, how could we turn each one of these patches into an embedding? Because that's our next step, right? We've got the number of patches dimension. If we're working towards going from a single input image, the input shape of 224, 2243, to an output shape of a single 1D sequence of patches, we've got 196. So we've got 196 patches, but we need to embed them into 768. How do we do that? What layer have we used in the past that slides over an image like a window? I'll give you a hint. We covered it back in PyTorch Computer Vision. And if you want to jump ahead, you can check out this animation. It'll give you a little hint. Oops. There we go. Spoiler alert. We're going to cover that in the next video. But if you want to jump ahead and try it out yourself, I encourage you to give it a go. I'll see you there.